The third lecture of our course is about cement, aggregates, and concrete. Let's start with cement. Cement in general is an adhesive and cohesive material which is capable of bonding together particles of solid matter into a compact, durable mass. Cement is a hydraulic material that sets and hardens both in water and air and turns into a stable product. When mixed with water, a plastic paste is formed. At the beginning, it is possible to give any desired form to this paste, but with time it begins to harden and loses its plasticity and gains strength against deformation. Setting starts when the paste begins to lose its plasticity, and it stops when the paste is stiffened. After the setting, hardening starts, and this process gives its mechanical strength to cement. Cement can be manufactured either from natural cement stones or artificially by using calcareous and argillaceous materials. The most common artificial element, cement, in general use around the world is Portland cement. This cement is made by heating limestone, which is calcium carbonate, with other materials such as clay to 1450 centigrade Celsius degrees in a kiln in a process known as calcination, whereby a molecule of carbon dioxide is liberated from calcium carbonate to form calcium oxide or quicklime, which then chemically combines with silica, aluminum oxide, and ferric oxide of clay to form calcium silicates and other cementitious compounds. The resulting hard substance, called clinker, grains with sizes 1 to 3 centimeters, which does not react with water and have a binding property, is then ground with a small amount of gypsum into a powder to make ordinary Portland cement. The name Portland comes from its resemblance to a natural stone quarry from Portland, United Kingdom. The grounded and powdered clinker is then cooled and stored in silos. Generally, cement is stored in bags of 50 kilograms. We have calcium oxide, quicklime, in the cement in the portions of 60 to 65%. It controls strength and soundness. Its deficiency reduces strength and setting time. Also, we have silicon dioxide, which gives strength to cement. Excess of it causes slow setting, and decomposition should not exceed 25%. Aluminum oxide is responsible for quick setting. If in excess, it lowers the strength, and it should not exceed 8%. Iron 3 oxide or ferric oxide gives the color. Magnesium oxide and some other materials can be found in cement. The degree of fineness of cement is the measure of the mean size of the grains in it. Resulting individual cement particles have a variety of angular shapes and a wide range of sizes. The sizes of a cement particle has an important effect on the rate at which it will hydrate when exposed to water. As it reacts, a layer of hydration products forms around outside of the particle, separating the unreacted core of the particle from the surrounding water. As this layer grows thicker, the rate of hydration slows down. Therefore, a small particle will react much more quickly than a large particle. Clearly, the particle size distribution is critical for controlling the rate at which a cement sets and gains strength. There must be a certain amount of small particles to ensure that the cement sets in a reasonable amount of time, but if there are too many small particles, the cement will set too quickly, leaving no time for mixing and placing. In a typical Portland cement, about 10% by weight of the cement is made of particles larger than 50 micrometer, and only few percent is particles larger than 90 micrometer. On the fine end, less than 10% of the cement is particles smaller than 2 micrometer.